Okay, so what we have in this problem is a chapter 13 problem, and in this case we have a mixture of gases that starts at a thermodynamic state 1, a pressure of 350 kilopascals and a temperature of 283 degrees, and then we move from a thermodynamic state 1 to a thermodynamic state 2 through an input of thermal energy. And when we get to state 2, we find out that this change of state has occurred at constant pressure, so both the volume and the temperature has changed. So in this case, the statements that this is P1 and T1, these again both refer to the pressure of the mixture and the temperature of the mixture at state 1, and then over here at state 2, these two are the pressure of the mixture and the temperature of the mixture at state 2. Now, the one thing that will change between state 1 and state 2, or I should say the other thing that changes, is that the volume of the mixtures will change, and those are not known but can be determined. So we'll state that the volume of the mixture, and I'm just going to explicitly state it as the mixture at 1 is 1 unknown, and the volume of the mixture at state 2 is also unknown. So I'm going to go in here, I think, and change these to be explicitly stating that this is the pressure of the mixture at state 1 and the temperature of the mixture at state 1. And we will state these again explicitly as the pressure of the mixture at state 2 and the temperature of the mixture at state 2. That the pressure of the mixture at any of the states will be the sum of the partial pressures. So the sum of the pressure of the oxygen plus the sum of the pressure of the carbon dioxide plus the sum of the pressure of the helium gas. As well, the volume of the mixture will also be a function of the component volumes of the oxygen, the carbon dioxide, and the helium. And the specific values of the given masses and the heat constant, the gas constants, and the specific heat at constant pressure are given over here in this table. So if we want to start at state 1, we can utilize the ideal gas law. And since we're given masses, we can utilize this form of the ideal gas law, PV equals mRT. So what we're going to do now is determine the volume at state 1 and at state 2, utilizing the ideal gas law. So we'll say at state 1, we will find out that the volume of the oxygen component will be mRT divided by P, and in this case, we're going to do this for each of the constituents, and the temperature and the pressure are going to be the same for all of these. So this is at state 1. I will write this first one out. So we have 0.1 kilograms of oxygen. Its gas constant is 0.2598 kilojoules per kilogram Kelvin. And we'll multiply that by its temperature at state 1, which is 283 Kelvin. And we will divide all of this by the initial pressure of 350 kilopascals. Now, when we work out this value, we will end up with a value of 0.21 cubic meters. Okay, well, before moving on, let's just verify that the units work out. So we have a kilogram times a kilojoule per kilogram Kelvin, and we're going to multiply this by Kelvin, and we're going to divide through by kilopascals. So in this case, my kilograms cancel, my Kelvin cancel, and we end up with a kilojoule. Well, a kilojoule is a kilonewton times a meter, and kilopascals are newtons per meter squared, or kilonewtons per meter squared. So my kilonewtons cancel, and I end up with units of, just kilonewton, you're writing out, meter times 1 over meter squared, which gives me my cubic meters. All right, so clearly our units work out. It's good to verify that the ideal, so clearly our units work out. It's a good thing to verify that our units do indeed work out, but I'm just going to erase those so that we can keep the solution notes a little bit easier to see. So likewise, I'm not going to write out all the steps, but the volume of the carbon dioxide is obtained the exact same way, and I'll just write out just the numbers. 1.0 times 0.1889 times 283 divided by 350. As stated, that term is going to be constant for all of these, and we're going to get 0.1527 cubic meters. And lastly, for the volume of the helium, I'm just going to write it down. So this works out to being 0.8397. So again, just to be clear, these are the partial or the specific volumes for each of the individual gas components. So to get the total volume of the mixture, we would add these together, and we will find out that the volume of the mixture at state 1 is equal to 0.021 plus 0.1527 plus 0.8397, and this equals 1.0134 cubic meters. Now you'll note that I'm keeping actually 5 significant figures because I know I'm going to need to subtract or utilize this in a calculation for the change in volume. Now, the only thing that changes between state 1 and state 2 with regards to our volume calculation is the temperature. So I can repeat this entire calculation at state 2 with the only thing changing is the temperature in the above equation. So the only change in the calculation is that the temperature changes. Only change in calculation is T mixture 1 was equal to 283 Kelvin, and this goes to T mixture at state 2, which is equal to 533 Kelvin. Okay, so by making those changes, or making that change and then recalculating everything, we will end up with actual change here. Is that we find out that the volume of my oxygen will be equal to 0.0396 cubic meters. The volume of the carbon dioxide becomes 1.5814 cubic meters, and the volume of the helium is equal to sorry, I wrote that down wrong, copied my. So the volume of the carbon dioxide is 0.2877 cubic meters. The volume of the helium is 1.5814 cubic meters, with the total volume of the mixture. Just move this down just a little bit so I have some room, will be the volume of the mixture at state 2 is then equal to 0.0396 plus 0.2877 plus 1.5814, which then equals a value of 1.9086 cubic meters. And then the first question asks us for the change in the volume of the mixture, so I can just write that up here, that the delta V of the mixture will equal the volume of the mixture at 2 minus the volume of the mixture at 1, which equals 1.9086 minus 1.0134, which will equal 0.896, which is the answer indicated in the problem statement. Okay, so now the last thing we want is the total amount of thermal energy that's been put into the system, and we can again utilize that. If we treat this as each component as an ideal gas, then the amount of energy required to change the volume of each of these, or change the temperature rather of each of these components, can be calculated individually. Or I can write this as Q total for the mixture will be equal to the sum over each component of the mixture times the mass of that component, the specific heat of that component, times delta T, going from T1 to T2. So we can calculate this, if I want to do it just as the summation, which is the way I'll write it, or we could figure out the total amount of energy for each component individually. But I can write this as 0.1, so that's the mass of the oxygen, times its specific heat, which is 0.918 from the chart, plus now the 1 kilogram of carbon dioxide times its individual specific heat, which is 0.846, and then the half kilogram of helium times its specific heat of 5.1926, and all of that then gets multiplied by delta T, which is 533 minus 283 Kelvin. And when I do that complete calculation, I will end up with 552 kilojoules per kilogram. I can also, since I know the total mass of this mixture, I can find out the total amount of heat. So Q dot total, or Q total, Q dot would be the rate. So Q total is just the total amount of energy in kilojoules, will be Q total times the total mass, and this will equal 883 kilojoules. So the answer listed in the problem statement wanted it in terms of kilojoules per kilogram, so the answer being 552 is the requested answer. All right, so again, this is a problem that took a mixture of gases from a thermodynamic state 1 and moved it to a thermodynamic of state 2. In this case, it was done at constant pressure, but you can envision other types where we would keep the volume the same and put energy in, so we would then utilize the change of energy would be mc sub v delta T if we had maintained the volume the same. Okay, so that concludes this problem, and the next video, or the other video, will show how we deal with a mixture as we move through a steady state device.